All right, here's the real lesson. So if we take a look, with this, we get into what's called the collision theory. Determining reaction rates or rate of reaction is based on several factors. The collision theory basically says that in order for a reaction to occur, the particles must collide. For example, if I keep a container of this particle over here, and I keep another container of this particle over here, they're not going to react. I've separated them, right? And we do this a lot of times in our house. We put things in storage bags and then we, put it on the shelves or whatnot. Now, that's to prevent bacteria from getting into it, mold spores from getting into it, all of these other things, right? We prevent the reaction from preventing the collision. Makes sense? All right. So in order for a reaction to occur, a collision frequency is a factor. So how often the reactant molecules collide? How can we affect collision frequency?
Increase temperature.
If we make the thing hotter, if we increase the temperature, what does that do to the particles?
They move faster.
Makes them move faster. She beat you. It's that mute button time. Time to hit that mute button. But increase the temperature, then particles move faster, which means they will collide more often. Right? They say that driving at faster rates increases collision. Same idea here. If we are moving the particles much faster, they're going to collide more. What's another way we can increase collision frequency?
Increase pressure, maybe?
Increasing pressure. There's a better way to say that.
Decreasing volume?
Decreasing volume. So imagine we have a certain number of moles, but now we have less volume. What has happened? We've increased the what? Molarity, which means we've increased the concentration. So that means that if we wanted to make these things go down, we could decrease temperature and decrease concentration by adding more solvent. Orientation is another big factor. That's a much more difficult one to actually affect. And the last one is energy, which was talked about, and that can be directly related to temperature. Remember, temperature is actually a measure of average kinetic energy. It's not a measure of, what do we say, hotness or coldness. It's actually more of a measure of average kinetic energy. So let's do this with a handshake. If we take a look, usually we actually have a handshake, but we're not going to do that today. I wish I had like a dummy hand. Do I have a dummy hand? That'd be cool. Yeah. I don't know. I think I'm just going to do it this way with a stick. So if we take a look, when you're shaking hands with somebody, the collision has to happen, right? So you have to have the collision, right? And that's going to allow for the handshake. Actually, let's just do it like this. I'll just do this. So my final thing is I want this. Here's the collision. And I don't know if you guys can do this, but this is my final thing that I want. What is it called? Banana Man?
No.
What is that?
No, it's like, I don't watch it, but there's jokes.
Yeah. Leo's probably saying something inappropriate. We got it on camera. I don't understand it, but all right. So we have the collision here. The orientation. If I collide here, is there any way I'm going to be able to do that? No, right? Did not get to that final thing. Orientation is important. They have to collide this way. They have to have enough, I have to have enough energy to get these fingers down. If I don't have enough energy to get these fingers down, it's not going to come together either, right? So they must collide They must have enough energy and proper orientation to get to this thing right here. That's the idea. Now, let's call this a successful collision to get to here. And then the final is going to be this. So this is the product I want. It all has to start from these things colliding with proper orientation, enough energy, right? And then the final exchange of electrons or whatnot. So we get to there. Now let me ask you this. Let's say that we have all of these things are successful. We have a successful collision. Any collision can result in that is successful, can result in the formation of products. Most of these collisions are not successful, and only 50% of successful ones. I can. This is why you don't use the chat. No. They don't even care at home. They're probably listening to their cuts now. 50% of these, there's 50% chance for even a successful collision with everything up here being successful, still not going back to make products. That's why most collisions are not successful. Because even if you get to here, right, anything could happen where you don't end up back here. Anything can happen where they do everything and then they're like, yeah, we're good. We're good as being the reactants. So that's why most collisions are not successful, because even the 50% that do collide, they still may go back to reactants. So that middle thing that's made, this thing, that is called the intermediate. Can you see my paper now? Books call it the intermediate, websites call it the intermediate. Sometimes it's called the transition state. It lasts usually for a fraction of a second. And the other thing that it's been called is the activated complex. And I think that this is what your book calls it, activated complex. So if you're reading your book, activated complex, some random website, you might see any one of these. I usually call it transition state or activated complex. It's some type of an intermediate thing that occurs between the reactants and the products. Basically, this is when electrons are being maneuvered around, switched around, forming different bonds. What factors affect the rate? Well, we kind of already got those. Temperature is a huge factor. That affects collision frequency and amount of energy. So it affects two things. If the temperature is increased for about 10 degrees Celsius, then the rate doubles, approximately. In AP, we'll figure out exactly how much it goes, but changes, but to this point, where it's gonna go, it doubles. So if the rate of reaction is 0.0012 at 20 degrees, then what is the rate at 30?
0.0024.
What's that? First? Somebody beat you here. And we go up another 10 degrees.
0.0048.
Definitely unmuting, I guess. 0.0048. I think I scared them all by threatening the detention or whatever it was I said. They'll calm down, or else lunch is finally getting to them. Well, what is the temperature of this room? You remember the thermometer over there? You want to check it out? You can get up. You don't have to stay seated. Is fine. So it's about 20 degrees Celsius in this room. And that's probably about 68 or something like that, 69. So 20 degrees Celsius in this room. What if we got the same thing? 0.0012 is the reaction rate. What if I drop down to 10?
0.0006.
Oh, they're gunning for you guys now. Yeah, 0.0006. What if we go down another? Yeah, what if we go down to very close to 0?
0.0003.
Right on time. Yeah, he's got that mute button ready now. So 0.0003. So if we take a look, let's think about that. This is 1/4 the rate it was at 20 degrees. Now most refrigerators will go down to about 4 degrees, 3.8, 4 degrees. They don't want to freeze because your lettuce and stuff like that can't handle that. That'll rupture the cell membrane, and then lettuce won't really be lettuce, right? It'll rupture that cell wall. Yeah, right, because it's mostly water. But what this means is if I can lay something on the counter for 1 day and it doesn't spoil, that means I can put it in the refrigerator and it will last 4 days, 1 day. So then it would be able to last 4 days. That means if I can set something on the counter for 1 week, then it will last 4 weeks. Right? So you can see that refrigeration is a process that is very important for food supply and food chain and stuff like that. Now we don't have to go to the grocery store as often. Now we don't have to go to all these other things. Now think about this, but then we take it down even another 10 degrees or another 10 degrees. Now, yeah, now this is the same temperature. About -18 is what they suggest everybody's freezer be at, right? Do you have a lukewarm freezer? Yeah. But what that's going to do is that's going to allow for, almost a year or something like that for some meats and stuff. But we're not talking about quality. We're just talking about bacteria and reactions with the bacteria being able to go through. But that's the big deal. That's a big, huge thing, right? That's what we're doing last today. So if we take a look, nature of reactants is also a big deal. That's why we learned the activity series last semester. We know that aluminum is more reactive than copper. So if you put aluminum in something, then it will react faster than copper if they both react with it. Just as if we put sodium in water, cesium reacting with the same amount of water, cesium would react much, much faster. Right? And we can attribute to it being much bigger and having that lower electronegativity. I'm sorry, having that lower ionization energy, meaning that those electrons are going to be able to be pulled off a lot easier. So nature of reactants has a part. Concentration of reactants. Right now, going down D Hall at 245 isn't that bad. But if you recall, years past, that hall was packed and it was very difficult. You were likely to collide with somebody and have a reaction because of just the sheer more amount of people. Catalysts. Catalysts, these guys right here, basically they help lower the energy requirement. Lower the energy requirement. So if we think about this as, let's say we have A plus B equals C. That reaction right there. Let's have a little more fun with it. Let's say that C is a date to the prom, right? Not this year, but next year. How many of you have a date to prom 2022? Date to prom, yeah. Probably not many people. So we're going to start with 0 right now. Owen is an outlier. But we're gonna start here. And we're gonna say this group of people is A and this group of people right here is B. We're not gonna assign anything other than just saying group of people. So as time goes on, what's going to happen to the groups of people that did not have a date? They will go down because they will ask people. Right now, you have a great chance. Because if you ask somebody, they can't say, I've already got a date. You'd be like, you're a liar, right? So the number of the group of people that don't have a date is going to slowly do what as we get closer to the date? It's going to go up, right? And the same thing, this is going to go down, and this is going to go down as well. And eventually, these all things will level out. And we will have the people going with a date, and we will have the people without dates, right? So as reactants are used up, just like as people get dates, products increase, just like the people, the couples, number of couples increase. Yeah, and as time goes on, there's less people that are going to be available to get a date with. Right? So let's imagine a few things. Let's say that we give, let's say we give both groups A and B $200 to help them get a date to a prom, right? There's going to be a lot more sky writings out there like, hey, so-and-so from group B, go to the prom with me. Or, you know, somebody's going to have somebody paint a mural or something like that down in Broad Ripple. All these different things, right? Or maybe somebody's going to, you know, they've had that chipped tooth in the front forever, and they get that chipped tooth fixed. Whatever it is. No, you fix your chipped tooth, and then it makes you more attractive. It's a, yeah, it's like, you know, a person without freckles is like a sky without stars, right? That type of thing. Is that what you're saying, or what? No, I'm not saying that at all. Please. But yeah, that's awesome. But basically, that's what temperature is. Temperature is energy. Maybe it's just you find more time to go and ask these people or whatnot. Maybe you spend all your time going around and just asking a huge number of people, right? That means that you're going to have to move faster or put time and energy into it somehow. Now, the nature of reactants, that's hard to change for our example here. But let's do concentration. Let's say all of a sudden that Carmel decides they're not having prom 2022 because of roundabouts. And they're just like, yeah, we're not doing it. Too many roundabouts up here. It's going to be too crazy. So they don't have prom, but the student council of North Central and the student council of Carmel get together and say, well, let's just have a big, huge prom. Well, what does that do to our reactants here? There's going to be more. So now there's a bigger pool, right? There's going to be more successful collisions, probably, hopefully, right? But what we're doing is we're taking these two up on the line. So what will that do with the line here? It would still be proportional, but it would increase, right? Yeah. No. The catalyst is coming up. So the catalyst, they used to do this around Valentine's Day, and I thought it was weird. It was a way for student council or somebody to make money, but they would give you this little bubble sheet, and you'd sit there and be like, you know, what is your favorite Harry Potter character? And you'd sit there and bubble it out, and then they would sit there and match it with somebody else's bubble sheet, and you're like, oh, we all love the big hairy guy. Yeah, I always thought it was weird, but yeah, people love that type of thing, right? That is the catalyst. The catalyst says, hey, I'm gonna, here's 5 people that you pair up with or whatnot. The matchmaker, you got it. Basically what the catalyst does is it reduces your energy involvement. So it would be like, the friend that sits there and says, hey, Timmy's sister has a crush on you, or whatever, right? You're like, what? Has a crush on me? You just saved me so much time looking for a prom date. Boom, less energy needed for the reaction to occur.
You probably just got one.
It's always easy the first day, right? Yeah, the notes are always easy the first day. So just keep that in mind. Like, this is an analogy only, but hopefully that helps you out a little bit. The cool thing is that whoever told you about Timmy's sister, they didn't get a date out of it. They got you a date. So that means that they can do that again. Probably not use Timmy's sister, but maybe Timmy has another sister or something. I don't know. But you know, they can sit there and hook another person up with another prom date. The catalyst does the same thing. It's not used up in the reaction. Boom, boom. So why does this, now the rate is actually the slope of this line. Now we could sit here and go into tangents. You guys do tangents and do instantaneous rates at particular times. But I don't know if we're going to do that. So this is time compared to concentration, independent variable. Time is independent of concentration, but concentration is dependent on time. As time goes on, concentration of these go down. So the actual rate is the slope. For example, you could make a graph that says time and money that you earned, right? So these are your work hours. This is the money that you earned. You could take money divided by time, change in money divided by change in time, and find your rate of work, right? Your hourly rate. That's all a rate is. It's basically a comparison of change in something to change in time. We are doing change in reactant concentrations or change in product concentrations over change in time. Let me ask you this. Why is it always weird to do change in reactant concentration?
Because it's negative.
Yeah, the rate for that would be negative, wouldn't it? Right? But the products are increasing as time goes on, so that rate is positive. So that's where we start out. As we said, it starts out easy. We will start out with the time interval method. We probably won't go with the instantaneous tangent method. But so we need concentration, which is molarity per second. This is another set of notes that we're going to do tomorrow, I think. So we want to go to page 4. So this is the time interval method. One thing I've talked to you about is delta means change. We've done delta T sub B, the change in boiling temperature. One thing I've briefly mentioned is how we can use brackets to talk about concentration. So the change in concentration of products divided by the change in time equals the rate. So what is the product in this reaction?
SO2 CO2.
SO2 Cl2. So if that's the product of the reaction, how would we fashion to show the concentration of the product? Little more than I asked for, but he said, he's actually answering this question. I just said the concentration of it, which would be shown by this. The change in concentration would be delta. Delta bracket SO2 Cl2. So this would be our actual formula. So yes, yes. So let's try one. A lot of times we do instantaneous reactions by rates by doing really quick ones next to, like, we're like, and done at a certain concentration. We find the time it happens. And then you just do this like from 0 to that, and you can get some decent data. But this one is going to allow us to get average overall and see how it is different from the start to the end. So from 0 to 10, and again, it's basically x2 minus x1 and y2 minus y1. What's that gonna equal? 0.246 divided by 10, which equals 0.0246 molarity per second. Again, if we were to look at this, we could sit there and find the slope for that first 10 seconds, and that would be it. This is the slope formula, right? No, just to find the slope. X2 minus X1, Y2 minus Y1. Yeah, yeah. So let's do the next one. So we want the next few seconds. So 0.355, and you can see if we were doing reactants that this would become negative. But time would still be what? Time would still be positive, which means that the overall rate would be negative. 20 minus 10 is still 10, and then we have 0.355 minus 0.246.
It's 0.109.
So then we divide that by 10, 0.0109 molarity per second. Good, good? Yeah. Because it goes like this. It doesn't have the same slope the whole time.
No, I know, but why?
Because of factors like, for example, we don't have, what is it doing? What is it doing over time? Is it faster, slower, or the same?
Lower.
Slower. It's slower because as this time goes on, just like the getting a date to prom thing, there's less reactants that are actually colliding successfully,
Oh, okay.
right? Because some reactants are hitting products. Can you go to the prom with me? I already got a date, right? That would be like hitting a product. And as time and time goes closer and closer to the end, right, when we call the reaction over or the prom is the next day, there's going to be a lot more products than, well, I shouldn't say that. Yeah, there's going to be a lot less reactants than there was at the beginning, right? Cool, cool. Basically, you can do those problems for this evening. And I think that is all I had for today. Just some practice work. I did want to say, remember that this is the stuff that you're like, oh yeah, this is easy. And then when it comes to test date, you're like, oh, I remember him saying something about that way back when, but you know, these are the points that are just as important as the other points. Cool, cool. Tomorrow, either we do a bunch of, I think tomorrow I'll do some demonstrations. Unfortunately for you at home, that's probably not as cool. Actually, that's gonna be your asynchronous assignment for Monday after spring break. I'm gonna have you to watch how to get a date movies.
How about if you bring in evidence?
Everybody's got extra credit, but you guys are having trouble getting the regular credit.
That's why we need extra credit.
You can't get the extra credit if you don't have the regular credit. That's all I got, guys. If you want to stick around and ask questions, I don't know why, but no, I'm just kidding. If you want to stick around and ask questions, by all means,